Now let us talk about thresholding. Thresholding is labeling pixel as belonging to one or two or more classes. In this case, you can have some threshold T, and in this case you can have two threshold T1, T2, and all those which belongs to one class, the other class. This may be, for this particular case, there may be three classes. So this is showing gray level histogram that can be partitioned by a single threshold and by a multiple threshold also you can use. So thresholding is actually a segmentation, kind of making classes so that the similar pixels or similar forming pixels, they can be categorized in some or the other way for final segmentation. This is the original image particular, and this is the image histogram of this. So you can see two different histograms all together and with different peaks. This is the result of global thresholding with T, which is somewhere midway between maximum and minimum gray levels. So you can see that these two images are not actually very much different, but still this is much the background and this structure are delineated quite well now. Now, this basic global thresholding, how it is done, this uses heuristic algorithm. We select an initial estimate of some threshold T, and what we do, we segment the image using this T threshold. G1 is the all pixel with intensity which is greater than T, and G2 are all the pixels with intensity which are less than or equal to T. Then we compute averages of this M1 and M2 of the pixels G1, G2. So number of pixels G1, number of pixels G2. We compute the average of this G1, M2 means average of this G2. And then we again find out M1 plus M2 by 2. And this is the new threshold. And we continue this again and again. We reiterate it and until there is no more change. So you can use this histogram to compute the averages. This is quite fast for computing these averages, right? Now this is the example. This is the original image. Now this is the image histogram. As you can see, again there are two different and well differentiated peaks. So this is the result of segmentation with the threshold estimated by the iteration, as I just indicated in the previous slide. Now we have optimal global thresholding also, because as we have seen that those threshold or that threshold was taken in between when the peaks were quite far away. But in this particular case, if we try to find out the threshold, or if we start with this threshold, what will happen that these pixels which should belong here will belong to this particular area or this segment, and these which should belong to this segment will ultimately belong to this. So there will be a false or you can say misclassification. So we want to pick a threshold that minimizes this error of misclassifying a point. What we do, we take E1t, that is from minus infinity to some threshold P2z dz, and then E2t, P1z is this P1z, this is the highest peak, and this P2z is for this. So what we do, from infinity to t, this to t, we take this, and from this t to infinity, we take this P2, right? This one. Now, unfortunately, we usually don't know this P, that is the probability distribution function P1z or P2z in advance. This is a problem. So this is the gray level probability distribution function of two regions in an image. So there is Otsu method for global thresholding, and what we do is we choose threshold to minimize the variance within the group. As PDFs are not known in advance, so we choose the threshold to minimize the variance within the groups. So this is the variance, and what we have done is this P1 as we have taken as sigma from I to k pi, and from k plus 1, this is one segment, this is another segment, k plus 1 to the final value, this is again the sum of pi. So we take this probability and we multiply it with this sigma. These are the variances of the first one, and this is the variances of the second one. Or rather, in the similar manner, equivalently, we can maximize the variance between the groups like this. Sigma b square will be equal to P1. P1 and P2 remain like this only. And M1 minus Mg, this is, the mid one, and M1 minus Mg, and this is again M2 minus Mg. This is the G for the whole image. So Mg is the global mean for complete mean, and this Mk is the mean of this class K. So we can take M1 is the mean of class 1, M2 is the mean of class 2. So you can also use MATLAB gray thresh function for this. This is Otsu's method for global thresholding. Now this is the original image. This is the histogram. These are high peaks were clipped by highlights detailed in the lower values. This is the segmentation result using the basic global algorithm, and this is the result obtained using the Otsu's method. Right? See the kind of achievement we have got in this, rather than if compared to the global thresholding. Then we have this multiple threshold. What does it mean? Otsu's method can be generalized into and to find multiple threshold also. So in the case of K classes, what we do, we maximize the between class variance. This is the between class variance. Mk minus Mg, K is from 1 to K. These are the number of classes, Pk. And Pk is nothing but the summation of Pi, and Mk, as you know, the I Pi by Pk. So this is the image of iceberg. This is the histogram. This is the image segmented into 3 regions using dual Otsu's threshold. So you can use multiple threshold also. Also, we have a variable threshold. What we do if this is a noisy shaded image, you say this area has more noise. This is its histogram. Now, if you do the segmentation, right? If you do the segmentation using the iterative global algorithm, we find that there is a misclassification. There is not a proper classification which we intended. This is the result which obtained from Otsu also. So neither our global iterative global algorithm, neither nor our Otsu can remove all these black spots from here. So what we can do, we can divide or subdivide this image into 6 sub images, and now apply Otsu in all these subdivided regions. So ultimately we can get a good result using this variable thresholding. Then we have this split and merge segmentation. What we do in this, we find a partitioning of connected regions such that each region has a consistent property. This property can be color or texture within it. So we partition these connected regions and then split and merge. Split regions that are inconsistent and merge and adjoining regions that are mutually consistent. So consistent, mutually adjoining regions are combined, or if they are not consistent, they are split. This is done until no further change is possible. This is split and merge segmentation. You can use some consistency property like this. Sigma and mu is always there. You can find sigma and mu from image very well. So this is the image of the Cygnus Loop supernova taken in the X-ray band by NASA's Hubble telescope. And these are the example of limiting the smallest allowed quadrigen to sizes of 32 by 32 and 16 by 16 and 8 by 8 pixels respectively. One more option is the Quadtree representation. Quad means 4. So Quadtree representation is recursively dividing the image into 4 quadrants. These are the 4 quadrants, and we stop dividing when each quadrant is consistent. If this is consistent, we don't further divide. If per se this R41 is not consistent, we divide it into 4. Again, if this is not consistent, we divide it into 4, and we go on like this. This is a very concise and efficient representation. Specifically, we used is for searching purpose. So this is the partitioned image. This is the corresponding Quadtree of this partition image. So the summary is, thresholding is a way to segment an image such that each pixel is labeled as belonging to one or typically 2 classes, and a global thresholding algorithm, it chooses a single threshold based on the image histogram across the entire image. Thank you so much. Take care.